Good morning all. This is Dr. Khalandar Basha, working as Associate Professor in Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss few questions related to the Module 5, which is ARM architecture under the course Microprocessor and Microcontrollers. Draw and explain the architecture of ARM processor. The figure shows the architecture of ARM processor. Here we are going to have a register file. All the registers from R0 to R15 we are having. Depending upon the modes, few will be used for special purpose, few will be used for general purpose. So out of R0 to R15, R15 is the program counter, which is going to point the address of the next memory, next instruction to be executed. So that address will be passed. For ALU, that is arithmetic logic unit, two values we require as operand. One will be passed through Rn. The second data will be passed through RM register. The RM register contents are given to the barrel shifter. The barrel shifter, depending upon the operation, like a shifting operation, something either towards left side or right side, the data will be sent to AL. If no pre-processing is taking place, directly RM will be passed to AL. So once the ALU operation is done, then the result, either it may be fed back to the register file or it may be sent to memory. So the address register will contain the address of the memory. After every operation, incrementing will be takes place. The next memory location address will be placed into address register. So apart from this ALU, we have MAC unit, which is multiply and accumulate unit, where it is going to take the values from RN register, RM register and accumulator. Next, here we have a instruction decoder. So depending upon the address which we are going to have in the program counter, that instruction will be fetched and it will be decoded. So whatever the data which you are going to place, that you can have a sign extension also. Next, when we are finding out or doing some processing in the ALU, the result will be stored in RD register. So for ALU operation, the input is given in RN register, RM register, either with or without pre-processing. After ALU operation, the output will be placed in RT register. So explain the pipelining in ARM processor. So pipelining is a mechanism where multiple tasks will be executed at the same time when resources sharing is not there. So with pipelining, the computational speed will be increases. Now we will see in ARM processor what are the various pipeline mechanism is existing. So the pipeline mechanism in RISC processor used to execute the instructions, which will speed up the execution by fetching the next instruction while other instruction being decoded and executed. So in ARM 7, it is having a 3-stage pipeline structure, which is shown in figure 1. In the 3 stages, the first stage is fetch, decode and execute. So fetch load the instruction from the memory. Decoding identify the instruction to be executed. Whereas execution process the instruction and write the results to the register. So figure 2 illustrate the pipeline using simple example. So in cycle 1, Let us consider the add instruction is fetched, where we don't have anything to be performed in decode phase and execute phase. In the next clock pulse, that is cycle 2, this add instruction will be go to the next stage, that is a decode phase. Now the fetch is empty, so the subtraction instruction will be enter into fetch cycle, and no operation will be done in the execution phase. In the third clock pulse, this add instruction will be changes from decode stage to execution phase, whereas that subtraction instruction will be enter from fetch to decoding phase. The next new instruction will be enter into the fetch cycle, that is compare. So for this case, if you observe, if you have a program which is consist of 3 instructions, add, sub, compare. So this add instruction, it had to go for fetch cycle, a decoding cycle, and executing cycle. Fetch, decode, execute. Fetch, decode, execute. So it has to perform these 3 instructions by the ARM processor. It requires 9 cycles. Whereas in the architecture, that is pipeline architecture, so here add instruction will be done in the cycle 3. In the next cycle, subtraction will be done. In the next cycle, compare will be done. So total only 5 cycles are sufficient. Whereas here we require 9 cycles. So if you see the number of cycles required for execution, so pipeline always will take a less number of cycles to execute. So in various ARM flavors, there are a different pipeline mechanism. So the pipeline design for each ARM family differs. In ARM 7, it is a 3-stage pipeline, which is a fetch, a decode, execute. Whereas in ARM 9, we have 5-stage pipeline, fetch, decode, execute, memory, and write. Whereas ARM 10, we have a 6-stage pipeline, fetch, issue, decode, execute, memory, and write. The next question is list and explain different data processing instructions of ARM 7. So the data processing instructions, mainly it is for moving the data. So here we have the 2 instructions for data transfer. One is MOV, another one is MVN. Here the syntax of the data processing instruction is the operation followed by condition followed by S, and here we have the destination, which is RD and RN operand. So the second operand is sent to ALU via barrel shifter. This is first operand. This is the second operand that will be sent to barrel shifter. The data movement does not specify the RN. Whereas for remaining arithmetic, logical, comparison, multiply instructions, RN may be present, but data transfer instructions, only 2 operands, that is operand 2 and odd. Next question, list and explain the register set of ARM processor. So ARM processors provide general purpose and special purpose register. The general purpose register hold either data or an address. They are identified with the letter R prefixed to the register number. There are up to 18 activate registers, out of which 16 are data registers, 2 special purpose registers, that is status registers we are going to have. So all these registers are of size 32-bit size. The data registers are visible to the programmer as R0 to R15, that is 16 registers. So the ARM processor has 3 registers. Out of these 16 registers, 3 registers are assigned with a particular task or specific function. The registers R13, R14, R15 are reserved for that. They are frequently given at different labels to differentiate them from each register. In addition to 16 register, there are two program status registers. One is CPSR and the one is SPSR. CPSR stands for Current Program Status Register. SPSR is Saved Program Status Register. So in all process, the following registers are available and accessible in processor mode. 13 a general purpose register, that is R0 to R12. R13, R14, R15 are specific purpose we are going to have, like a stack pointer, a link register, program counter. One application register, that is APSR. Next, these registers, depending upon the modes of operation, availability of registers are shown in the figure. So in the user mode, we are going to have the registers R0 to R15 and CPSR. Whereas in FIQ mode, R0 to R7 and R15 and CPSR registers. These are reserved registers. Next, IRQ. In the user mode, we are going to use R0 to R12, R15 and CPSR register. In SVC mode, R0 to R12, R15 and CPSR is used. In UNDEF mode, user mode R0 to R12 will be used and CPSR is used. Abort mode, in the abort mode R0 to R12, R15 and CPSR is used. For thumb state, up to this point, that is the upper 8 registers will be used as thumb state low register, and from R8 to R15 that will be considered as thumb state high registers. Next, list and explain different arithmetic instructions of ARM processor. So the arithmetic instructions implemented addition, subtraction of 32-bit signed and unsigned values. The various instructions we are having is add, ADC, RSB, RSC, SUB, SBC. The syntax of this instruction is instruction followed by condition S, RD, RN and balance shifter output, that is N. So the add instruction, it is used to perform the addition of the content in Rn and N, where N is the barrel shifter output. These two datas, that is Rn register, will be added with the N and the result will be stored in RT register. Next one is ADC. This is used for add two 32-bit values along with the carry flag. The syntax of this instruction is ADC, RD, Rn and N. So this instruction will add the content of Rn register with the barrel shifter output, that is N, along with the carry flag, and the result will be stored in RD register. The next instruction is RSB, which is reverse subtract of two 32-bit values. The syntax of this instruction is RSB, RD, Rn and N. So here the subtraction will be takes place. The barrel shifter output with Rn register contents and the result will be placed in RD register. The next instruction is RSC, which is reverse subtraction with the carry of two 32-bit values. The syntax of this instruction is RSC, RD, Rn and N. So here the contents of Rn are subtracted from barrel shifter output, that is N, along with the complement of the carry flag, and the result will be stored in RD register. Next instruction is sub instruction. This is subtract two 32-bit values. The syntax of this instruction is SUB, RD, Rn and N. Here N is subtracted from Rn register and the result will be stored in RD register. SBC, which is subtract with the carry of two 32-bit values. The syntax of this instruction is SBC, RD, Rn and N. Here the contents of N are subtracted from Rn register along with the carry flag and the result will be stored in RT register. So at a glance, all the arithmetic instructions we have studied are ADD, that is addition along with the carry, reverse subtraction with carry, subtraction with carry. Next, describe about ARM instructions, load store instructions and software interrupt instructions. So when we are discussing these instructions, here we are going to discuss these two terms also, that is pre-indexing and post-indexing in ARM processor. So now we will see the pre-indexing with the write back addressing mode. Let us consider we have instruction R0, R1, #4, where the base address we can take as R1, #4. Here R0 register is 0, R1 register is 00090000. Let us consider the memory which we are having at the address is 9000 is 01010101, whereas in 9004 location 02020202. Here, as it is pre-indexing R1, what is the current address? 9000 will be added with 4, that is 9004 is the current location. This 9004 location contents will be copied into R0 register for LDR instruction. So after executing this LDR instruction, the 9004 data will be copied into R0 register. So after executing this, R1, that is address, will be updated with R1 plus 4. This is pre-indexing with write back. In contrast, the pre-index offset is the same as the pre-index with the write back, but does not update the address base register. So LDR R0, R1, R4. So here R1 plus R4, that is the memory location data, will be copied into R0 and R1 will not be updated. Right? The pre-index mode is useful for accessing an element in a data structure. So after this memory address, if exclamatory mark is there, then it is pre-indexing with the write back. If we don't have this exclamatory mark, this indicates it is not with write back. Next, pre-indexing. In the pre-indexing, we are not going to consider the write back. So as it is a pre-indexing, R1 plus 4, R1 content is 90,000 or 00090000 plus 4. This memory location contents will be copied into R0 and R1 will not be updated. Whatever the previous address is there, the same address it is going to take place. This is pre-indexing without write back. Next, we will see the post-indexing. The post-index only update the address base register after the address is used. So here we will take the example LDR R0 R1, #4. So when you are represented this #4 outside of this memory, that you can consider as the post-indexing. First, R1 memory location content address, that memory location content will be copied into R0. After copying, then this 4 will be added to R1 address and R1 will be updated with the added value, that is 90000 plus 4, that will be copied into this. So now here we can see the single register load addressing modes. The pre-index with the immediate offset, pre-index with the register offset, pre-index with the scaled register offset, pre-index with write back with an immediate offset, pre-index write back with a register offset, pre-index write back with scaled register offset, immediate post-indexed, register post-indexed, scaled register hold. The next are software interrupt, that is SWI. The software interrupt instruction causes a software interrupt exception, which provides a mechanism for applications to call operating system routines. The syntax of the instruction is SWI condition, which is optional always, the software interrupt number. So when the processor executes an SWI instruction, it sets the program counter to the offset value 8 in the vector table. The instruction also forces the processor mode to SVC mode, which allows an operating system routine to be called in a privileged mode. So each SWI instruction has an associated the interrupt number, which is used to represent a particular function call or feature. So when SWI instructions are executed, the functionality it is going to carry out is the LR SVC will contain the address of the instruction following the SWI. Then SPSR SVC is loaded with the CPSR. The program counter with the vector address plus offset value as 8. And CPSR mode will be changed to SVC. And CPSR I is equivalent to 1, which will mask IRQ register. Since SWI instructions are used to call operating system routines, you need some parameter passing. This is achieved using registers. The next question is describe about the ARM instruction, program status register instructions, load constant and conditional exception. So the program status register instructions, the ARM instruction set provide two instructions to directly control a program status register, that is PSR. The MRS instruction transfers the contents of either CPSR or SPSR into a register in a reverse direction. The MSR instruction transfers the content of a register to the CPSR or SPSR. Together, these instructions are used to read and write the CPSR, current program status register, and SPSR. The syntax of the instruction is MRS or MSR, conditional, which is optional, then RD, the CPSR or SPSR. So these register contents will be copied into RD. Whereas in MSR instruction, the CPSR along with the fields and RM register are to write what is the immediate data that we are going to write in immediate data. So in the syntax you can see labels called as fields. This can be any combination of control, extension, status and flags. So the fields related to particular regions of PSR is shown in figure. Next one is loading constants. So there is no ARM instruction to move the 32-bit constants into a register. Since ARM instructions are 32-bit in size, they obviously cannot specify a general 32-bit constant. To aid programming, there are two pseudo instructions to move 32-bit value into a register. These instructions are LDR and ADR. LDR is load constant pseudo instruction. ADR is load address pseudo instruction. Now we will see LDR instruction, which is a load constant pseudo instruction. The syntax of the instruction is LDR RD comma equals to constant. So load a constant pseudo instruction writes a 32-bit constant to a register using whatever the instructions are available. So it defaults to a memory read if constant cannot be encoded using other instructions. So whatever the constant, which is a 32-bit size, will be loaded into RD. So example, LDR R0 is equivalent to FF. So this R0 register will be loaded with the FF. It is same as that of moving FF into R0 register. The next instruction is ADR, which is load address pseudo instruction. The syntax of the instruction is ADR RD, label. This loads address pseudo instructions write a relative address into a register, which will be encoded using a PC relative expression. So here, whatever the label which I am specifying, that address will be loaded into RD. So the ADR instruction or address relative instructions place the address of the given label into the register RD using PC relative add or subtract. Next we will see conditional execution. So the conditional execution depends upon two components. One is condition field, the second one is conditional flags. So the conditional field is located in the instruction, whereas the conditional flags are located in CPSR register. So let us consider example, add instruction with the equal condition appended. This instruction will be executed only the 0 flag in the CPSR is set to 1. So here the condition which you are placing, it is always optional. If condition is specified, if the condition is true, then only the concerned operation will be performed. So only comparison instructions and data processing instructions with S suffix appended for the mnemonic updates the flag in the CPSR. So if S is not there, then updation of the flags will not be taken place. So explain exceptions and interrupt vector table. So when an exception or interrupt occur, the process suspends the normal execution and starts loading instruction from the exception vector table or interrupt vector table. The process set the program counter to a specific memory address. So in ARM, the various exceptions or interrupts we are going to have are reset, undefined instruction, software interrupt, free fetch abort, data abort, reserved, interrupt request, fast interrupt request. The address we are going to have mentioned in the address field as well as high address. So each vector table entry contains a form of branch instructions pointing to the start of a specific routine. So reset vector is the location of the first instruction executed by the processor when the power is applied. So this instruction branches to the initialization of the code. Undefined instruction vector is used when the processor cannot decode an instruction. Software interrupt vector is called when we execute SWI instruction. The SWI instruction is frequently used as the mechanism to invoke an operating system routine. Next one is free fetch abort. This vector occurs when the processor attempts to fetch an instruction from an address without the correct access permissions. The actual abort occurs in the decoding phase. Data abort vector is similar to free fetch abort, but it is raised when instruction attempt to access data memory without correct access permissions. Interrupt request vector is used external hardware to interrupt the normal execution flow of the processor, raised if IRQ are not masked. The next one is fast interrupt request. A vector is similar to interrupt request but is reserved for hardware requiring fast processing response systems. So it can be raised if FIQs are not masked in the CPSR register. The next question is explain branch instructions for ARM process. So a branch instruction changes the flow of execution are used to call a routine. The various branch instructions are branch, branch with the link, that is BL, branch with exchange, BX, branch exchange with the link, that is BLX. So the syntax of these instructions you can see. For branch instruction, branch optional conditional label. So B label. So it will jump to the label specified whenever the ARM processor encounters this instruction without checking any condition. For BL instruction, that is branch with link, the syntax of this instruction is BL condition label. So the BL instruction is similar to branch instruction but overrides the link register LR with a return register. So PC, that is program counter, is going to be placed with the address where the condition, the control has to be transferred. So after execution where it has to return, that address we are going to be loaded into link register. Next we have the instruction is branch exchange, that is BX. The syntax of this instruction is BX optional condition RM. The branch exchange instruction uses an absolute address stored in the register ARM RM. It is primarily used to branch to and from thumb code access. So the T bit, that is thumb bit in CPSR, is updated by the least significant bit of the branch register. So here the program counter is going to be loaded with the RM register ANDed with FF, 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 FE, and the thumb bit will be ANDed, thumb bit T will be given with RM and with 1. So the T bit in CPSR is updated by the least significant bit of the branch register. The next instruction is BLX, which is branch exchange with the link. The syntax of the instruction is BLX condition label RM. So the BLX instruction uses an absolute address which is stored in RM. It's primarily used to branch to and from thumb access, thumb code address. So the BLX instruction updates the T bit of the CPSR with the least significant bit. Additionally, sets the link register with the return address. Next, explain thumb instructions. The ARM contain only one instruction set, that is 32-bit set. In the thumb state, the processor simply expand the smaller shorthand instruction fetched from the memory into their 32-bit equivalent. The difference between two equivalent instructions lies in how the instructions are fetched and interpreted prior to execution, not in how they function. So the expansion from 16-bit to 32-bit instruction is accomplished via a dedicated hardware within the chip. It does not slow execution even a bit. But the narrowing, the 16-bit instruction do offer memory advantages. The thumb instruction set provides most of the functions required in a typical application. The arithmetic logical operations and the load, store, data movements and conditional and unconditional branch instructions are supported in thumb mode. Based upon the available instruction set, any code written in C could be executed successfully in thumb state. However, device drivers and exception handler must often be written at least partially in armed state. So in this session, we have discussed the questions related to the module 5, which is armed processor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.